Now, we do have some prerequisites for conducting Wi-Fi security tests, like having some hardware. But don't worry, these aren't expensive tools. It'll be enough to have a PC and a Wi-Fi USB adapter to complete this training. Now, the most important thing to watch out for when buying a USB Wi-Fi adapter is that it has monitor mode and allows you to inject packets. Now, based on our experience, we can say that the chipset of most of the Wi-Fi USB adapters sold on the market do not have these features. You can use one of the Wi-Fi adapters listed in the table during the tests. So in fact, we use the TP-Link TL-WN722N high-gain wireless USB adapter as our hardware throughout the course. The TP-Link high-gain wireless USB adapter allows you to connect a computer to a wireless network and access a high-speed internet connection. It provides wireless speeds of up to 150 megabits per second. It is compliant with IEEE 802.11n and gives you a more robust wireless signal than existing wireless 802.11g technology can provide. It has the ability to reduce data loss over long distances and through obstacles in a small office or large apartment. And it automatically avoids channel conflicts using its clear channel assessment technology, and this is greatly enhancing our wireless performance. It also supports WPA, WPA2, as well as WEP encryptions to protect the wireless network efficiently. So to get better signal performance, the adapter's 4 dBi high-gain external antenna can be rotated and adjusted in different directions to fit various environments. The adapter has a quick security setup that allows you to almost instantly set up your security. Just by pressing the QSS button, it'll establish a WPA2 secure connection. So I'll use the TP-Link Wi-Fi adapter in this course, but of course there are other hardware and wireless auditing platforms for Wi-Fi pen testing that you can use for the course, like Pineapple and Fruity Wi-Fi. The Wi-Fi Pineapple is a piece of hardware that was originally created for network penetration testing. Wi-Fi Pineapple allows pen testers to perform targeted man-in-the-middle attacks, advanced discovery, credential gathering, open source intelligence gathering, and more with a web interface. Now, Fruity Wi-Fi is an open source tool to audit wireless networks. It allows the user to deploy advanced attacks by directly using the web interface or by sending messages to it. Initially, the application was created to be used with Raspberry Pi, but it can also be installed on any Debian-based system. Now, I am true to my word when I say that I'll be using lots of tools for attacking Wi-Fi networks. You might be familiar with some of these as they are the most often used. Some of them are the more advanced tools for Wi-Fi pen testing. So what we like to do is use a bunch of different tools, in fact, using as many different tools as possible for different attack scenarios, thereby introducing you to how to use each one of them, including the ones that you know, and hopefully introduce you to a whole bunch more that you haven't even heard of before. We'll explain all this in detail shortly, but I just want to let you know that we will be installing the tools before using them in the upcoming lectures. So we're not going to install all of them when we set up our laboratory. So here we're going to use aircrack-ng. And aircrack-ng consists of a detector, a packet sniffer, WEP, and WPA, WPA2-PSK crack and analysis. It includes airmon-ng, airplay-ng, aerodump-ng, airbase-ng, and packetforge-ng. Sounds like fun, huh? Yes, we're going to be using all these tools. Wifite. Now, Wifite runs existing wireless auditing tools. Wifite is designed to use all known methods such as WPS pin attack, WPA handshake capture, as well as web attacks. BetterCap. Now, BetterCap is a powerful, flexible, and portable tool created to perform various types of man-in-the-middle attacks against a network, manipulate HTTP, HTTPS, and TCP traffic in real time, sniff for credentials, and so much more. Fluxion. So Fluxion is a security auditing and social engineering research tool. It attempts to retrieve the WPA2 key from a target access point by means of a social engineering attack. You might know that as phishing. Hashcat. So Hashcat is a type of hacking tool, and it's a password cracker specifically. It was created to be able to hack the most complex passwords, targeting multiple aspects of coding simultaneously. But what we're going to be using Hashcat for is for cracking WPA2 by using GPU in this course. Here's a favorite, Wi-Fi Pumpkin. Now, the Wi-Fi Pumpkin is a rogue access point framework. It'll easily create fake networks, all while forwarding legitimate traffic to and from the unsuspecting target. We're going to use something called Kismet. Kismet is a wireless network and device detector. It's a sniffer, and it's a war driving tool. And Cowpatty. So Cowpatty is a C-based tool for running a brute force dictionary attack against WPA keys. Now, hopefully you're as excited as I am because this is some very rich content, yeah? So why don't we just get started? We'll set up the laboratory next. All right, so before we start, we'll plug in the Wi-Fi adapter to Kali and check the connectivity. So first, we'll start the Kali machine. Log in with default credentials, Kali and Kali. Now plug in the Wi-Fi adapter to the host machine. So let's look at the devices on the top left menu. And there are Wi-Fi adapters and my USB converter on the list. So click the name of the Wi-Fi adapter to connect the virtual machine. And now let's double check on the terminal screen with the LUSB command. And sure, the adapter is there, but the adapter's light is still not on. I don't know if you notice that. So I will run the iwconfig command. Now it's similar to ifconfig, but it is dedicated to wireless interfaces. So it's used to display and set the parameters of the wireless network interface. But you see that there is no wireless network interface here. So in order for VirtualBox to recognize our USB devices, that means that we've got to add the user to the VirtualBox users group. So why don't we go ahead and list the groups that my user belongs to. Groups $user, and there is no VirtualBox user group here. Sudo user mode -a-g vbox users Kali. And if there is no group named VirtualBox users, why don't we create it? Sudo add group vbox users. So now we can add the user to this group. Okay, so now let's go back and look at the groups again. All right, you see how that works. Now we've got to reboot the machine, but I'll shut down just to adjust the USB settings. So let's go to the settings of Kali, click Ports and USB. Now, naturally, there's a more permanent solution that captures the device as soon as it's inserted into the host. So while the Wi-Fi adapter is plugged in, we can create USB device filters for each device. So I'll create new filters for my Wi-Fi adapter and MacBook USB connector device. Click OK. Now unplug the Wi-Fi adapter and start up Kali again. Log in with default credentials. Now, plug in the Wi-Fi adapter again. Let's have a look at the devices. And yeah, the devices are still there. But I will also check with LSUSB and IWconfig again. But there is no light. Well, I guess VirtualBox does not recognize the adapter because my MacBook USB converter device supports USB 3.0. So I'll change the USB controller and make it 3.0. Okay, so finally the light is on and VirtualBox recognizes the wireless interface. So if you're using a USB converter device, remember to change the USB controller for your particular device. Now, if you're using VMware, these steps are pretty easy. First, start the Kali machine. Log in with the default credentials, Kali and Kali. Now plug in the Wi-Fi adapter to the host machine. VMware asks for your choice to connect the adapter. Select Connect to Linux. Then open the terminal screen. First, we'll switch the user to root with sudo su-. Do not write sudo for every command that requires root privileges, right? All right, so let's run lsusb, and that'll display the information about the USB buses as well as the devices connected to Kali. And sure enough, here is our Wi-Fi adapter. So now let's run the iwconfig command. WLAN 0 is the name of the first wireless network interface on the system, and it displays the details of our Wi-Fi adapter. Great, so we see detailed information about the concepts here in the next lecture, so don't worry about it now. But we will look at the connected USB devices in VMware settings. So let's go to the toolbar. Click the settings icon and select USB and Bluetooth. And here you'll find a list of connected USB devices. And you can also see them here to make sure your device is connected. IEEE 802.11. So the IEEE is an acronym for Institute of Electrical and Electronics Engineers. It was formed way back in 1963. Now, they're a group of scientists, engineers, and allied professionals who together are the leading authority in aerospace, telecommunications, biomedical engineering, electrical power, etc., etc. The IEEE is separated, however, into various committees. So the 802 committee develops local area network, or LAN standards, as well as Metropolitan Area Network Standards, or MAN standards. The IEEE 802.11 is a set of wireless LAN standards developed by the IEEE Working Group 11 in 1997. The 802.11 family consists of a series of standards and amendments, but I'll explain the main and the widely accepted ones. So first we have the original IEEE 802.11 standard released in 1997, and it defined the rates of 1 or 2 megabits per second on 2.4 gigahertz band. Then 802.11b standards were created in 1999. It'll provide 5.5 and 11 megabits per second rates on the 2.4 gigahertz band. Now come on, they're only just getting started. The IEEE 802.11a That was released around the same time as 802.11b. 802.11a uses the 5 gigahertz band. Now, the 5 gigahertz band has way more channels that are available, and they do not overlap like those in the 2.4 gigahertz band. So then, moving through 2003, IEEE 802.11g was introduced and extended throughput to up to 54 megabits per second using the same bandwidth as 802.11b. And it just so happens it's backward compatible with IEEE 802.11b. Now, IEEE 802.11i is an amendment to the original IEEE 802.11. It implemented Wi-Fi Protected Access 2, or WPA2, released in 2004. So the standard specifies security mechanisms for wireless networks. Then they were able to deprecate the wired equivalent privacy, or WEP, because it had security vulnerabilities. So then in 2004, work began on IEEE 802.11n, and that increased transfer speeds and provided more range on 2.4 gigahertz and 5 gigahertz networks. So that brings us to 2009, when the final release of 802.11n was completed. So IEEE 802.11n is an amendment, and it builds on previous 802.11 standards by adding multiple input, multiple output, or MIMO, right? MIMO is a form of antenna technology that uses multiple antennas to enable signals traveling via different paths as a result of reflections and all the other types of interference. They can be now separated, and their capability is used to improve the data throughput and/or the signal-to-noise ratio, thereby improving system performance. Now, some of the basic terminologies, these are going to be very important for us to understand the following lectures, so I just want to make sure that we're on the basically same page, right? Because you're going to hear these concepts in any resource about Wi-Fi networking, and of course, throughout this course. Now, if you already know the basic terminology, sure, you can go ahead and skip to the next lecture. So an access point, an AP. This is a device that serves as a central wireless connection point for a Wi-Fi network. The Service Set Identifier, or SSID. It's the name of the wireless network. It can be contained in the beacons sent out by access points, or it can be hidden. So the clients who wish to associate must first know the name of the network first, right? So early security guidance was to hide the SSID of your network, but modern networking tools can detect the SSID simply by watching for a legitimate client association, because SSIDs are transmitted in clear text. BSSID, Basic Service Set Identifier. It's a unique address that identifies the access point or hub that creates the wireless network. The Extended Service Set Identifier, or ESSID, it's the name of the wireless network and is used by all APs that provide access to the same infrastructure in an extended service set. It can be advertised by APs and their beacons, or suppressed so that clients must know the ESSID before associating with an AP. Roaming. So in a wireless network with multiple APs, a client that is moving from the coverage area provided by one AP to that provided by another is called roaming. So it must disassociate from the first AP before it can associate to the next AP. A channel. This is the network path for wireless transmissions. Each Wi-Fi standard has numerous channels, each of which is a specific central frequency. Data rate. The rate in which data can be transferred at any given moment to and from a device. Most times, the incoming and outgoing data transfer rates affect each other adversely. For example, if you're uploading a video while loading a web page, the web page will load slower than usual due to the upload usage. A beacon is transmitted by an AP 10 times per second, and it advertises the existence of the AP on a particular channel or channels. It includes information needed by clients to associate, as well as it may include the ESSID, the supported channels, as well as data rates, and whether it's open or requires authentication. Now, decibels can also be used to describe antenna power levels. A decibel is the basic unit of measurement used in Wi-Fi radio signals. dB specifies a difference or ratio between the two signal levels, and is used to describe the effect of system devices on signal strength. So a dBm is the dB value compared to 1 milliwatt of power. For example, if the signal power is 100 milliwatts and the reference is 1 milliwatt, the value of the decibel becomes 20 relative to a milliwatt. Make sense? So our TP-Link adapter's antenna has 4 dBi signal power. Now, a suffix indicates that the reference value is often appended to the decibel symbol. The suffix is I because I refers to an isotropic antenna, which is equally sensitive to signals from all directions. The gain is a key performance number, and this combines the antenna's directivity and electrical efficiency. So in a transmitting antenna, the gain describes how well the antenna converts input power into radio waves headed in a specific direction. There are two main wireless operating modes: infrastructure and ad hoc. So in the case of wireless networking in infrastructure mode, you are connecting your devices using a central device, namely a wireless access point. To join the WLAN or wireless LAN, the AP and all the wireless clients are configured to use the same SSID. The AP is then cabled to the wired network to allow wireless clients to access, for example, internet connections or printers. Additional APs can be added to the wireless LAN to increase the reach of the infrastructure and support any number of wireless clients. So compare or contrast this to ad hoc mode networks. Now, this makes wireless connections directly between computers. Infrastructure mode wireless networks use networking infrastructure. So in this case, infrastructure refers to switches and routers, firewalls, access points, or APs. Infrastructure mode wireless networking is the mode that you'll most often encounter in your work as a networking professional, supporting networks for clients or in a corporate or enterprise environment. At a minimum, the only network infrastructure component that is required for infrastructure mode is an access point. But if an AP is all you have no more than you would have when you're using ad hoc mode. However, most infrastructure mode applications and implementations include other components from, just traditional network infrastructures. On Linux-type operating systems, acting as a station, namely a client, is usually called managed mode, and when acting as an AP, it's usually referred to as master mode. An ad hoc network consists of at least 2 stations communicating without an AP. This mode is also called peer-to-peer mode. In an ad hoc network, one of the participating stations takes on some of the responsibilities of an AP, such as beaconing and the authentication of new clients joining the network. So in ad hoc mode, the station taking on the responsibilities of the AP does not relay packets to other nodes like an AP does. Monitor mode is not really a wireless mode, but it is essentially important in attacking wireless networks. In a nutshell, monitor mode allows a wireless card to monitor the packets that are received without any filtering. So monitor mode is essentially the promiscuous mode, if you will, equivalent for wireless. In both cases, actually, you see all the packets going across the wire or channel. Now, when using some wireless drivers, this mode allows for the sending of raw 802.11 frames. This mode is important for reading packets from the card, analyzing them, and updating the user interface as it determines new information. It doesn't transmit packets themselves. Instead, it listens to all the packets on a given channel and then analyzes those packets to see just what's going on. So if you and your neighbor share the same channel, when you put your card into monitor mode to see what's going on in your network, you're going to see their traffic as well. So why don't we go ahead and see how to enable monitor mode of the wireless network card in Kali Linux. So we'll go to the Kali machine and plug in the Wi-Fi adapter. That goes into your host machine. Open the terminal screen and switch the user to the super user. So you got to do that first. Now let's see the status of the adapter with the iwconfig command. So its mode is managed right now. So we can enable monitor mode with a script airmon-ng. So if we run this command without any parameters, it lists the status of the wireless interfaces. To enable monitor mode, run airmon-ng start WLAN 0. And as you can see, before enabling it, we must kill the processes of the network managers with the airmon-ng check kill command. So now let's try to run the previous command again. And it doesn't work now because we killed the processes of the network interfaces. And then WLAN 0 is switched to monitor mode. All right, so let's have a look at the status again. And there it is on monitor mode now. And the name WLAN 0 became WLAN 0 mon. So to disable monitor mode, just run airmon-ng stop WLAN 0 mon. And now it's changed back again. So after these steps, please note that we must restart the network manager. So service network manager start. And then finally, let's check to double ensure that the network manager is up and running. And sure enough, everything looks okay. Very cool. All right, so let's begin our journey by looking at the structure of an 802.11 MAC frame. So a MAC frame is constructed of common fields and specific fields. So I'll quickly provide a short explanation of each. All right, so MAC frames consist of three main structures. The frame body is a variable length field. It contains information specific to individual frame types. FCS stands for frame check sequence. All right, so it's an error detecting code that's added to each frame. And in the MAC header, there's a frame control section. All right, so the very first two octets transmitted by a station are the frame control. Protocol version. Now this will provide the version of the 802.11 protocol used, and the value is currently 0. We also have type and subtype. These will tell you what the function of the frame actually is. So there are three different frame types of fields: control, data, management. There are multiple subtype fields for each frame type, and then each subtype determines the specific function to perform for its associated frame type. So to move on, To DS and from DS indicates whether the frame is going into or exiting the distribution system, all right? More frag indicates whether more fragments of the frame are to follow this one or not. Retry indicates that the frame is being retransmitted. Power management indicates whether the sending STA is in active mode or power save mode. WEP indicates whether or not the encryption and authentication are used in the frame. Order indicates that the frame is being sent using the strictly ordered service class, right? Now, the field is usually not set. Duration ID indicates the time on the channel that the sender is assuming to be occupied from the end of the current frame. Now, here are some different cases of the fields of addresses depending on the communication between the station and the access point. Sequence control is used to recognize frame duplication by setting the sequence number of each frame.